Okay, so good morning to all the participants. So here I am going to talk about some calculus of Rn, and this will be done geometrically. So well, we are familiar with the idea of derivative for real valued functions of real value. If I take a point A and suppose the limit of f of a plus h minus f of a upon h, if this limit exists when h tends to 0, we say that the function is differentiable at the point A, and this is in fact a real number we denoted by f dash a. So the derivative of a function f dash a is in fact a real number for functions from R to R. This definition is known to us. Here our problem is to extend this idea for functions from Rn to Rn. One can see that this definition as such will not work for functions from Rn to Rn. The simple reason is that here if I take my domain to be Rn, then the division by a vector will not make sense. And therefore what we do, we try to generalize the thing, we try to look at it geometrically and will generalize the idea of derivative for functions from Rn to Rn. In the first step, what we observe is that even if I replace the codomain by a vector space Rm, that my definition f of a plus h minus f of a upon h in the limiting case makes sense. This definition makes sense because this scalar, this h is a scalar, and these two quantities are vectors. So the difference of two vectors is a vector, and dividing by h it remains a vector. So if this limit exists, this resulting quantity will be a vector quantity. This will be a vector in R. So the major thing is that for real valued function of the real variable, the derivative of the function at A is a scalar, whereas for vector valued function of a real variable, the derivative is a vector in Rn. Now, in order to generalize this idea for Rn to Rm, what I will do, I will see it geometrically. So there are some observations. Let me rewrite the above expression as limit h tends to 0 f of a plus h minus f of a minus f dash a into h upon h. This is equal to 0. When the function is differentiable, this limit of the quotient is 0. Now what you observe over here is that this quantity is a linear function of h. So in fact I can say, if I denote f of a plus h minus f of a, this is in fact a non-linear change in f. I will denote it by the symbol delta fah. And this quantity will be rewritten as delta fah minus this linear function of h, we will call it f dash a into h upon h. Limit h tends to 0 is 0. So at this point I will say that a function is differentiable at the point A if there exists a linear map f dash a into h such that the difference between the non-linear change and the linear change goes to 0 faster than h. In fact, I have to explain over here what do I mean by saying that this quantity tends to 0 faster than h. If you have two real valued function of a real variable, say fx and gx, suppose these two functions are real valued function of a real variable, and the limit of f when x tends to 0 is 0, as well as the limit of gx when x goes to 0 is also 0, then one can think of the limit of the quotient fx upon gx when x goes to 0. Now this limit may or may not be 0, it can be infinite as well. Now if this limit comes out to be 0, you will notice that this f tends to 0 faster than the function in the denominator. For example, if I think of the function x cube upon x square, these are two functions of x. Now you can notice that this limit is 0. The reason is that the numerator goes towards 0 faster than the denominator function. I'm sorry. So, okay. So what I was telling you is that a function is differentiable at a point A if the difference between the nonlinear chain and the linear chain goes to 0 faster than h. We can see it geometrically. Suppose I have a function f from an interval into R3, then the graph of this function f will be a curve. Now suppose a point A is here and there is another point A plus h in the interval. Their images, suppose they are point A, its position vector will be the vector fa. The image of the point A plus h will be another point over the curve. Its position vector will be f of A plus h. And the difference between the two, that is delta fah, will be this vector AB. So from the figure, this delta fa is in fact equal to the vector AB. And when h goes towards 0, this chord AB will tend towards the tangent. When h goes to 0, the point B will move towards the point A, and in the limiting case, this will become the vector at the point A. I will call it f dash A into h, or I will be rather calling it dfh. So this quantity f dash A into h is a linear function of h, and we will call it differential of f at A is a function of h. So now what I am demanding geometrically is that the difference between this and this should tend towards 0 faster than the h. So we have noticed this quantity, this thing in our curves theory also. For example, if I have a curve in space and if I think of a vector which touches it at a point, then this difference doesn't go towards 0 faster than the distance along the curve. It will happen if the line tangential to the curve is close to the curve. That is why it is said that the derivative of the function is a linear approximation of the curve itself. Look at this curve. In a small neighborhood of the curve, you can see that these two quantities are approximately the same. Okay, now if this happens for two functions, what we write that f is little o g. So if this symbol is written, we will read it like this, that when f and g both tends to 0, f goes towards 0 faster than g. This is just a symbol. Okay, so under this notation, I can say that delta fah minus f dash a into h is equal to little o h. Okay. Or if you want to expand it, it can be rewritten as f of a plus h equal to f of a plus f dash a into h plus oh. Now, this is in fact known as Taylor formula. This is the Taylor formula up to order 1. This is called the Taylor's formula, where this OH is called the remainder term, and about the remainder term we say that it contains terms which goes towards 0 faster than h. So this becomes our definition. I will say that a function f from R to Rm is differentiable at a point m if there exists a linear map, we denote it by dfa from R to Rm, such that the difference between the nonlinear change and the linear change goes to 0 faster than h. So this becomes our new definition. In fact, it's a reinterpretation of our old definition. This is our old definition. I will always refer it as number 1, and this Taylor series definition I will call as definition number 2. These two definitions are in fact equivalent. Alright, now moving forward, there was one reason why we tried to generalize it. The first reason was that this h is a vector quantity for functions from Rn to Rn. Even if when I make change over here, and instead of writing h in the denominator, if I write modulus of h, still definition remains valid. But the problem is in the limiting process. For example, if I assume this to be the definition for functions from Rn to Rm, then you will notice, for example, if I consider a function f from R2 to R, say f of xy equal to under root 1 minus x square minus y square. This gives a hemisphere in R3, a hemisphere whose center lies at the origin and its radius is 1. So this is, I'm drawing the full sphere, but it is simply a hemisphere. If you think of drawing a tangent plane at the point 0, 0, 1, then I can regard this plane, tangent plane at 0, 0, 1 as the plane which is obtained by taking the limit in case of a general plane passing through 0, 0, 1, and suppose x1, x2, f of x1, x2. Suppose this is one point, there is another point on the sphere, say y1, y2, f of y1, y2. Now suppose if x1, x2 tends towards 0 as well as y1, y2 tends towards 0, what I expect is that the tangent passing through these points will become a tangent plane at the point 0, 0, 1. But this won't happen. In fact, it will depend how x1, x2 and y1, y2 tends to 0. What path they go from x1, x2 to 0, 0, etc. This may not tend towards this tangent plane, and therefore this definition will fail for function from Rn to Rm. So not only this was the difficulty that h cannot be a vector quantity, in fact otherwise also there is a problem in the limiting process as well. Alright. Now, in fact, whatever I have done over here, in fact, this is a third, which I stated verbally, that f is differentiable if and only if there exists a linear map. Now, I will ask the other way. If there exists a linear map such that the difference between the nonlinear chain and the linear chain tends to 0 faster than h, then will the function be differentiable? The answer is yes. One way we have already shown that the answer is true. Suppose now the converse problem. Converse problem. The converse problem is if there exists a linear map, there exists a linear map. Given already a function, given a function f from R to Rn, and if there is a linear map, once again say I will call it LA from R to Rn, such that f of a plus h minus fa minus LAH upon h, this limit h tends to 0 is 0. Suppose this condition holds. Let me call it a star condition. Suppose I have a function from R to R, and suppose I have a linear map from R to Rm, and this condition holds, then I can ask myself, is the function f differentiable? Is the function f differentiable at A? This is the question. The answer is yes. The answer is yes. We can prove it. Look, what I will do, I will start with this assumption and the star equation. Then here what you see is, now look here, since this is a linear map, I am saying it's a linear map, and you know that if whenever you have a linear map from one vector space V to another vector space W, then it can always be expressed as Tx equal to Ax. Every linear map looks like this. And this is a matrix. Suppose this is m-dimensional vector space, this is n-dimensional vector space, then A is always an m by n matrix, where X is a n by 1 matrix. You can call it a column vector or an n by 1 matrix, it's the same. So all linear maps are defined in this manner. So in this case, I am saying that LA is a linear map. So LA must be written as LAH equal to some m by 1 matrix, into this H should be a 1 by 1 matrix. I scale. Is it right? So I will write down this as m by 1 means a m rows and 1 columns. So this implies f of a plus h minus f of a minus, I will write down A into H, where A is some m by 1 matrix upon H, limit H tends to 0. This must be 0. By a star condition, this should happen. Now let me rewrite down this as f of A plus H minus f of A upon H, limit H tends to 0, and minus AH upon H, the limit. Now H will be cancelled out. What will be left is only A. So what you get is that this quantity is equal to. So once you reach to this step, you will say that this limit exists, which is a vector, and its value is A m by 1 matrix, and I will call it the derivative of f at A, because this quantity is known as the derivative of f at A, which turns out to an m by 1 matrix. So the converse is also true. That means the derivative exists whenever a star condition holds. So whatever I have said over here is in fact necessary and sufficient. So this formula in fact defines the derivative for functions at least from R to R. Alright. Now, there is, when you see in this formula 2, this term OH appears and we call it the remainder term. Whenever you write a Taylor series, this last term is known as the remainder term. There are several expressions for the remainder term. Now we will look into it geometrically. So, this is the remainder term. In fact, the way we are defining the derivative of a function, I will introduce another function eta a. So what I do, so what we have noticed, we have observed that if f is differentiable at a, that if f from R to Rn is differentiable at a, then the function eta a, which I am defining here, is a function of h. I will write down this as f of a plus h minus f of capital F. We are using minus f of a upon h minus f dash when h is non-zero and it is equal to 0 when h equal to 0. You can see if f is differentiable at a point a, f dash a will exist, and therefore this function eta a defined in this manner will always be continuous at h equal to 0. So if f is differentiable, then this function is continuous at h equal to 0. Look here, how could I find out this function eta a? Look here, this corresponds to what? This corresponds to the chord of the graph of the function, whereas this is the tangent. What I am demanding is that the difference between the chord and the tangent should go on becoming 0 and 0, and when h becomes 0, the chord must coincide with the tangent. And this process must be a continuous process. When you go from chord to the tangent, you should go in a continuous manner. So that is how this function appears. Now, if I rewrite down, and the converse is also true. If f is differentiable, this eta is continuous at h equal to 0. Now the other way around, if I write down some scalar over here, some vector quantity over here, and write down that this is continuous, the function will be differentiable by virtue of formula number 2. Now let us rewrite down. So when you will read down, you will write down f of a plus h minus f of a minus h times f dash a or f dash a times h, and this h in the denominator, it is equal to eta ah. Right? Or you better write down this as mod h. These two are equivalent. Whether you write h or mod h, the definition remains true. So what follows from here, that f of a plus h is equal to f of a plus f dash a into h plus eta ah into modulus of h. So the Taylor series has been further simplified. Now this in fact the remainder term. And what happens is that this remainder term is 0 at the point 0 and it is a continuous function on R. So this is what the Taylor formula is. Alright. Now this I will take as the definition of the differentiable function in the most general case. Alright. Now what we notice is from this last formula, what we can notice is that this f of a plus h minus fa, we are calling it the nonlinear change. This is the nonlinear change in f. Whereas you have brought this term into the left hand side, in the right side you are left with f dash a into h. You are calling it dfah and plus some eta in h into modulus of h. This is 0 at h equal to 0, and at other places it is continuous. Okay, so what you see is that delta fah is in fact approximately equal to dfah. Is it right? It is not exactly equal. It is equal to this plus something else also, but approximately in a small neighborhood of h. When the values of h are very, very small, these two quantities will be equal. So that is why we say that the derivative of a function is a linear approximation of the function itself. So this is the reason we say that the derivative of f is a linear approximation of f. And as I have shown, if you think of a curve, in fact the graph of f is always a curve in our case, and this is a tangent line f dash a or dfah, and this change from here to here is delta fah. You can see in a small neighborhood these two are same. Alright. Okay. So whatever characterization we have got, we will take as a definition for function from Rn to Rn. So I will say if f is a function from an open subset of Rn into Rn, then I will say that f is differentiable at the point of omega if f of a plus h is equal to f of a plus a linear function dfah plus a continuous function multiplied by modulus of h. Everything makes sense for function from Rn to Rm. The difficulty of division by vector etc. have been removed, and now in place of that these linear functions have appeared. This is in fact equal to the matrix f dash a into h. This is continuous function of h. Now this f dash a is in fact an m by n matrix. What is this? This is an m by n matrix. And what is h? H is coming from Rn, an open set of Rn. So every vector in Rn can be think of as an n by 1 matrix. And this product between f dash a and h is in fact the matrix multiplication. This has to be kept in mind. Now what you observe over here is that the derivative of a function from Rn to Rm is actually an m by n matrix. So this fellow, an m by n matrix, is called the derivative of f. Okay. So the interpretation of the derivative changes from space to space. When you were working with functions from R to R, the derivative was simply a scalar. But when you consider functions from R to Rn, the derivative was a vector. Now in the most general setting, when you think of functions from Rn to Rm, the derivative is simply an m by n matrix. Now if I remove these n and m and I will take them R1, then this matrix will become a 1 by 1 matrix. A 1 by 1 matrix means simply I scale. Now the next problem is the computation of this derivative. For function from R to R, the computation was easy. We had developed techniques to find out the derivative of a function. But for functions from Rn to Rn, the computation is that of a matrix. So what do? We start with some, to understand how to compute the derivative, I will start with an open subset of R2. So this is some rectangle. What you do is you consider a surface. So suppose I have a surface z equal to fxy. That means I am considering a function f from where to where? From an open subset of R2 to R. Now if you look at the graph of this function, it will be drawn in R3. The domain I will take over here, suppose this domain is some omega, an open subset. Let me take it a rectangular domain, no problem. So what I am doing, I am taking points in this rectangle and the image is a real number over here. So if you draw the graph means the collection of all point x comma y comma fxy. The collection of all such points is the graph which comes out to be a surface. Okay, so what I will view it is as if the rectangle is sitting over here and this surface is the image. This is the graph of it. Graph of small f. Okay, now this function, I will call this function as capital F. So f is a function from an open rectangle of R2 to R3. The surface is sitting in R3. How does it map? It maps like this. F of xy is equal to xy comma f of xy. Okay. So instead of dealing with f, I would prefer to deal with f so that I may see things geometrically. So first of all, you consider a point A. I have to find the derivative of capital F at a point A. Now think of a line passing through A. Okay, suppose this is a line which passes through, this is line L, suppose. This passes through A and suppose it is parallel to some vector V. Okay, so an arbitrary point on this line will be some A plus T times vector V, am I right? You go on varying small t, you will go on getting different points on the line N. Now what you do next, you just restrict f onto this line capital L. Then the restriction of f will be nothing but the image of this line. For example, if I have this sheet and if I draw a line over this sheet and if I curve it, then the line will be curved and the image will be simply a curve. Is it right? And the image of the point A will be some capital F A. Okay. All right. Now what I will do, let me call this curve as some gamma t. A is fixed, V is fixed, what varies is t. So a function of a single variable always gives a curve in the space. So the image of this f is in fact a curve which happens to lie only on the surface, sigma, whatever you call it. Now let me think of the derivative of gamma at the point A. So I am denoting f of L, I am calling as the curve gamma t, or to be more specific, gamma vt. Now what I am going to do, I will first find out the derivative gamma dash at the point A, or t equal to 0, because the function, so let me suppose this corresponds to t equal to 0. This point A corresponds to t equal to 0. You go on increasing the values of t, you will go on getting different points of the line. So gamma dash 0 will be what? It will be gamma t, gamma vt minus gamma v0 upon t, limit t tends to 0. This is how you define the derivative of a curve. Is it right? Now what is gamma Vt? Gamma Vt is f of L means a L की जगह क्या लिखूंगा a plus TV. This is a f of a plus. I am identifying L with arbitrary point of L as a plus TV. So this is f of a plus TV minus f of t equal to 0 will give you f of a upon t with the limit when t tends to 0. You can recognize this expression in the right hand side. Everybody knows that this is nothing but the directional derivative of f evaluated at the point A. So this is remarkable that the derivative of this curve gamma is nothing but the tangent vector of this curve gamma. Okay, so what you do, you go on drawing several other lines also passing through A. Every time you will be getting some curve, and every time you can draw tangent vector. What we expect that the totality of all these tangent vectors will generate the tangent plane. Why we are interested in the tangent plane? Because in the case from function from R to Rm, we have observed that the tangent line is responsible for everything. The tangent line becomes the derivative for a curve. So we expect that the tangent plane for a surface must be the derivative. So the plane that has come up is maybe a tangent plane. So that is what now we are thinking, that this plane will be the tangent plane. All right. So what I am doing is I am considering the collection of all dVFA with V belonging to R. And I am expecting this to be, let me call it some LA. Now I expect this to be a tangent plane, but a tangent plane is a linear space. Everybody knows that a tangent plane is a linear place, but this may or may not be a tangent plane. So this will be a plane if it is the image of a plane in a R2. Is it right? So this is a plane. This may be a plane. This may be a plane. This LA, I mean, this means LA. Maybe a tangent plane, maybe a plane first, maybe a plane. If it is the image of a linear space under a linear map. Under a linear map. The image of a linear map of a linear space is linear. That is why I'm thinking of this as a plane or a two-dimensional space. So we need to demand. So this is what we demand. अच्छा हम ये कह रहे हैं कि this is the image of a linear space. So the Rn is already a linear space. So that is why we demand. So we require. So we require that there we require that there is a map. That there should be a map. That there should be a map. There should be a linear map. Let me call that linear map as LA. From what to what? From where to where? From Rn to Rm. Such that LA of V equal to dvf. So we require such a map. And once this map exists, the image of this plane will be an image, will be a linear map over here. Is it right? So now there is one more thing that has to be done. You see the plane about the in the setting of curve, what we notice that some line may touch the curve, but that line may not be tangent. So the requirement was that this line, if it is tangent, the difference between this line and the curve should be the smallest, in the sense that this difference should go towards zero when edge goes towards zero faster. In fact, so this requirement is equivalent to saying that this plane made of dvfa should closely sit with the surface. So this is one requirement. Also, we require number two, that this plane, which plane? This LA. This plane LA sits closely to the surface. At A. Look, there is a possibility that there is a plane passing through the point FA, but it is not in fact tangential to the surface. It may be a little more tilted than we require. So in order to make it sit tangentially, we need to make some other changes. And this requirement is equivalent to saying that the difference between the nonlinear change and the linear change should go towards zero faster than h. Okay, so whatever requirement we had in the first case, in our earlier definition from R to Rm, now becomes a necessary and sufficient condition for a function to be differentiable from Rm to Rm. Okay, so this is a matter of observation. These requirements were part of the definition for functions from R to Rm. So what we noticed for a differentiable function, f, small f from R to Rm, now becomes our necessary and sufficient condition, now becomes necessary and sufficient condition for a function f from Rm to, and that necessary and sufficient condition is equivalent to, that is, f is differentiable at A if and only if, what happens? If and only if there exists a linear map. ये वाला linear map LA. If and only if there exists a linear map. BF from R to R, Rn to R. Such that f of A plus h minus f of A minus dfah upon modulus of h in the limiting case is zero. This condition you have seen is equivalent to saying that f of A, there exists a continuous map at 0 also, such that f of a plus h plus dfah plus eta into modulus of h. If f is differentiable, there exists a Taylor series which consists of the linear map and a continuous map satisfying this Taylor formula. So now these two, either first one or the second one, are the formulas for the function to be differentiable, are the necessary and sufficient condition for the function to be differentiable. Alright, now we will make use of these box formulas to check the differentiability of some known function. For example, in the setting for functions from R to R, we know that the derivative of a constant function is 0. The derivative of a linear map is the function itself. Now the same thing should be verified for functions from Rn to Rm. How much time I have left here? Okay. So I have got, for example, if I look at these simple examples, for example, if I have a constant function, suppose select f from Rn to Rm be a constant function, that is f of x is equal to some fixed vector b. This is fixed vector b of r. So all vector x of Rn are mapped to b, means it's a constant function. So y derivative will be 0, so I have to see this. So f of a plus h will be what? F of a plus h is b. This is equal to b. And f of a is what? It is also b. Is it right? So means if this is b, means other things are 0. So means dfah plus eta eh, this must be 0, this must be 0. So 0 map is a linear map. 0 function is a constant, is a continuous function. So means the Taylor series for this function is satisfied, this Taylor series, and therefore I will say that f is differentiable. And what is its derivative? The derivative is f dash a into h. So this matrix must be a 0 matrix. Then only you will get a 0 over here. So this, the derivative of a constant map is a 0 matrix for functions from Rn to Rn. This was a simple fact, but we need to verify everything from Taylor's formula. Now there is another thing, that is a linear map. These are some simple examples for functions. So if I consider f a function from Rn to Rn, I can think of any function, but since these spaces are linear, there must be some linear map between them also. If you are thinking of linear map, the domain and the codomain should be linear maps. Suppose I take a point A, so it is always differentiable. A linear map is always differentiable. That we will check it up. So f of a plus h will be what? It is f of a plus f of h, according to the linearity of f. Now, okay, fa I will keep as it is. F of h I can multiply it by what? By n by 1 matrix, say constant vector 1. 1 means 1, 1, 1, 1. Okay. So let me write down as 1. Okay. Plus some 0. Okay. Now, if you read this, you will say that Taylor series is satisfied. Because this is a continuous function. This is a matrix and it is multiplied by this. So what type of matrix? This is an n by n type matrix. So Taylor series is satisfied. Taylor series is satisfied. Okay. And what is the derivative? Derivative is fh. Derivative is fh. So this implies that the derivative of f is same as f itself. This implies dfh comes out to be equal to what? It comes out to be equal to f of h. How do you define dfh? You define dfh equal to f dash a into h. H is now in our case is 1. So this is dfah, this comes out to be f of x. So there is no difference between dfa and f, and therefore for a linear function, the differential of f is same as f. So these are known facts, but we can verify it through the Taylor's formula, which is our definition now. All right. Now there are some simple results which I can write down as theorems. The first theorem is if f is, now there are two kinds of derivative, differential of f and the directional derivative. So if f is differentiable, all directional derivative exists. This is one of the results. But if all directional derivative exists at a, in all direction, the function may not be differentiable. So it is true only one way. If f is differentiable, in our sense, if f is differentiable at a, then all directional derivative at a exists. If f is differentiable at a, then all directional derivative of f is always a function from R into R, or some open set of R into R. Okay. So how to prove this? And the relationship between the two is dfa of a vector v equal to dv. This will be the relationship between the directional derivative and the derivative of the function. Okay, so look here. We have noticed for the proof, we know that dfa is a linear map. So if dfa is a linear map, I can write down this as what? I can write down dfav. Let me compute what? dfav. It is equal to f dash a into v. So in fact, since f is differentiable, okay, since f is differentiable, according to this definition, what will happen? Differentiability. F of a plus h minus f of a minus dfah upon h modulus of h limit h tends to 0 is 0. Okay, so what I will do, I will put h equal to t into v. Mind it, h is a vector of R. H is a vector of R, and every vector I can write down some scalar times some other vector. Is it right? So I can always write down the vector h as t times some other vector v in the same direction, of course. So this expression will be written as f of a plus tv minus f of a minus dfh. You told me it is f dash a into v. Okay, and v you are writing as what? You are writing f dash a into v means h, f dash a into h. H means t into v. Or, already got it. You better write down dfa of h means tv. And t being scalar will come out. dfa is linear, so it is divided by mod of tv. So it means mod of v into t, and the limit when h tends to 0, if and only if t tends to 0. So I can replace the limit by this t tends to 0. Now read it again. Okay, so I will take mod of v out in the limit. So this is equal to 1 upon mod of v, limit t tends to 0. I will break it into two parts, f of a plus tv minus f of a upon t, mod v is already out, minus, now when you will divide it by t, it will remain only dfav. Is it okay? Okay, both the term have been divided by t, mod v is out, 1 upon mod v is out. So what you are left is 1 upon mod v. Now the limit of this is nothing but dvfa, dvfa minus this is dfav. This is 0. Right side is 0 all the time. Since mod v is non-zero, so I can say that dvfa is equal to dfa. So whenever f is differentiable, directional derivatives are always ensured. And the relationship between these two derivatives is this. Alright, this is one of the results. And there is another result. But the converse is not true. In order to show that the converse is not true, you need to just give an example where the converse doesn't true. So I will just remind you of the converse. Of the converse, we have an example. There is a famous example of function of two variables. It is xy square upon x square plus y to the power 4 when xy is non-zero and 0 when xy is. You can see that the directional derivative in all directions exists, but the function is not continuous, even what to say of differentiability. So perhaps 1 hour is over, so I stop at this point. And for the problems, I will be available on the link. So those who want to ask any question or any queries, they can ask. So thank you very much.